So this is our first lecture on equilibrium and collision theory. And this is the how of chemical reactions, right? So delta H and delta S tells us why reactions occur, because they are releasing energy or moving towards more disordered state. And so that can predict whether it will happen. But this is the process, the how. And what we see is that molecules are objects, right? And as they interact with each other, sometimes they can react and sometimes they won't. And when they react and how they react depends on a number of factors. And these are our three main factors that we understand in collision theory, which is the theory that helps explain how reactions occur. And basically they say, look, if you want atoms or molecules to react, first of all, they have to collide. They have to come in contact with one another. And hopefully that's not a huge surprise to you, as we saw with ionic and covalent compounds. We were looking at either giving away electrons or sharing electrons in different ways. And to do that, you would have to come in contact, right? It's not like sodium can take his electron and dump it in the mail and chlorine can pick it up and be like, gee, thanks, guy, right? Like they have to actually come into contact for that electron transfer or the electron sharing process to happen. So that's really important. Next, we have the specific orientation, and this is part of why we studied the VSEPR theory, right? Because we know that molecules have specific shapes, and then looking at it from a different orientation gives you different results. So for instance, we have these two molecules coming together. You might think of these as like H2 and F2, right? And what we want to happen is H2 plus F2 goes to form HF, like S, for instance. And if we balance this equation, we'll see that one molecule of H2 and one molecule of F2 is going to give us two molecules of HF, right? So if we're looking at that in terms of these molecules, we'll say that the red is the H2 and the blue is the F2. If they collide like this, then this one guy can't react with either of those, and this other fluorine would be left out in the cold, so it wouldn't work, okay? So there has to be like a really good orientation. This has a better orientation. They're coming together. It looks like this HF could run away together and this HF could run away together. But the third thing we need is a sufficient amount of energy. So here is showing this is a hydrogen molecule with sufficient energy. Here is a fluorine molecule with sufficient energy. And because they have sufficient energy, it allows them to separate like this and go on to form products. So you have to collide, which is what we see in each of these cases. You have to have specific orientations, which is what we see in both of those cases. And you have to have sufficient energy. This is checking all of the boxes. Do you guys see what's going on there? All right. So the way that you're going to remember this, I usually encourage my students to remember this, is I look at this like a good kiss, right? So tossing kisses from afar, blowing kisses is not, I mean, it's cute, but it's not like a really good kiss, right? For a really good kiss, you have to have contact occur, right? We're all adults here, right? Contact occurs. And there's got to be a specific orientation. Like, has anybody ever gone in for a kiss and the person like turned their head at the last moment and you like got their cheek or maybe their ear? And you're like, okay, not a good kiss. There's a specific orientation that has to happen in order for this to be a good kiss. And then finally, there's got to be like a sufficient amount of energy, right? So it's not like kissing your brother, kissing your grandma or something. If your kiss is going to create like a chemical reaction, right? If there's going to be any chemistry between you and the other person, there's got to be like a little energy in it, okay? That's kind of cheesy. It's better if I can see your faces. We can chuckle about it. Nobody has to admit that they've ever gone in for a kiss and had their hair turned here, but that's kind of how you want to think about it. That'll help you remember the specific collision theory, I hope. Does that make sense? Are you guys with me? Okay, so good. In order to increase the rate of reaction or the possibility of a reaction occurring, there are some things that we can do that exploit what we know about what it is that atoms need. Okay, so let me move these over here. We'll address some of these. It is really awkward when they turn last minute, and sometimes they don't mean to. But sometimes something happens, well, and they kind of turn. But anyways, all right. So some things that we can do that can help make our reaction happen faster. Let's make it. Okay, so we can stir a reaction if this is in solution, a reaction is occurring in solution, then stirring it or shaking it is going to increase the rate of collision, right? Because we're just basically forcing additional collisions to occur. And so when we force additional collisions to occur, then we increase the likelihood that one of those collisions will be in the right orientation and have sufficient energy. Does that make sense? Whoa, hold on. Okay. All right, so that's the first thing we can do. Another thing we can do is, I'd say in our kissing example, you might say, you know, what if you made all these people go on speed dates or something? You're going to increase the chances that you're going to get some people who are going to end up having a reaction there. Okay, next we could increase concentration, right? This, again, works in solution. And then of course, what that's going to do is if you have more particles per, milliliter, then you're going to increase again the number of particle collisions, the rate. This is like the formation of singles wards, right? That's a cultural thing we can all touch, right? So you take all of the single people in a church and you put them together in a big room and be like, all right, have a good chat, y'all, right? And so we're just going to increase the concentration, and that's going to increase the number of collisions, and that might actually increase the chances that something will happen as a result. Okay. All right. We can increase the pressure. This is basically the same thing as increasing concentration, but for gases instead of solutions, right? So if you're in the gas phase, then when you increase the pressure, you're just pressing all of those gas particles closer together. So again, it does the same kind of a thing here. Let's see. Increases collisions. Okay. D. Another thing we can do here, we can add heat. All right. What would adding heat do for us? It's going to speed up the molecules, right? Because heat is molecular movement, right? So it does two things. It increases says molecular movement, which is going to increase collisions, right? But it does something else as well, and that is it gives everybody a little bit of extra energy, right? So a little bit of extra energy means that your collisions that occur in the right orientation are more likely to have sufficient energy to help it form a product, right? So this also adds energy to the molecules, which helps you with the number 3, which is you need that sufficient energy. Okay, excellent. This might be like you take all those single people and you put them in a club downtown, right? And everybody's moving and it's dark and it's fun and everybody's having a really good time. And so you're more likely to make a positive connection when you're feeling good and you're moving around a lot. Does that make sense? Okay. Our last option here is to add a catalyst. right? And what catalysts do is something really interesting. It doesn't make a reaction occur that wouldn't otherwise occur usually, but it makes a reaction go really fast. And usually what it does is it says, you don't need this sufficient amount of energy. I'm just going to help like hold your hand and guide you through the process, right? So like for instance, in our dating example, this might be like if you hired a fancy dating team that's going to screen everybody for you and then like introduce you only to people who are like perfect matches and set you up on like really romantic dates so that the ambiance is all there. And so it's just really easy to use. Another really good example would be like alcohol, right? So if you're out dancing on the floor and you add alcohol to that, then it might be that you're looking at some person that you would not have ever considered kissing before. And you're like, hey, it looks pretty good now, right? That's right. Liquor is quicker. So that's our analogy here. So adding a catalyst is going to lower the amount of energy required. So that helps us overcome that sufficient energy barrier more easily. Because now you need less energy to get over that energy barrier. Okay, catalysts are really interesting. They're not consumed in the reaction. They remain behind after the reaction takes place. And they are so important biologically. Basically, all of the enzymes in our body, they're catalysts for important chemical reactions. They would not happen fast enough for life to exist, basically, otherwise. So that's a really important thing. Okay, so there's one thing that'll help us kind of understand this in terms of kind of a picture, another picture. We can use an energy diagram to help us see what's happening in our reaction. So an energy diagram is a little graph like this, where we're mapping the amount of energy available in the system versus what's happening at the reaction level. We'll call it the reaction coordinate, which is just saying as we go from reactants to products, how much energy do these things have? So you might say, look, my H2 and my F2 molecules together have a certain amount of energy, this level. And my HF products have less energy than that, right? And so you'd think it would be easy to just go straight downhill. They should just spontaneously do it. But the reason that they don't is because of this energy barrier, okay? I have to go through a high energy transition state, this guy right here, which is kind of weird and uncomfortable and not as low energy as this state. But I have to go over that high energy state to get to the lower energy state. Does that make sense? And this helps explain what we talked about on Tuesday, where we said spontaneous for chemistry doesn't mean it's just going to happen all by itself. It means that it will continue to happen all by itself after it has been started, because this is the little start, right? This is the spark that it takes. And anytime you start a combustion reaction, you need a little spark, but once you get it going, it's going to go all by itself, okay? This is shown an exothermic or a negative delta H or negative delta G reaction because the final energy is lower than the initial energy. But it still is not going to go over that hump unless it's got enough energy to get there. Does that make sense? Okay. And essentially adding heat gives more of these molecules enough energy to go over the hump, but adding the catalyst lowers the hump itself and basically says, let's take this path. Ooh, that's a lot easier to get over. Okay, so there are a few things that we can tell by looking at an energy diagram, right? If the products are lower in energy than the reactants, then we can tell it's spontaneous because everything is going to flow towards a lower energy state if given the option, right? So that's one thing to look for. Let me say this. If products are lower energy than reactants, reaction is spontaneous. Okay. Whereas the reverse is true, right? If higher, then non-spontaneous. The other thing that we can look at here is the height of that hill here. If the hill is really high, then we can say, look, even if it's technically spontaneous because the products are lower in energy, because it takes so much energy to get over that hill, it's not really going to happen. Or if it does, it goes really slowly, right? So the height of this hill is directly related to how fast that reaction will occur, right? A low hill is really easy to go over, whereas a high hill is really hard. So a low hill indicates a fast reaction, and a high hill would indicate a slow reaction, right? We call this hill, I keep calling it a hill, but it has a special name. It is the, right here, the difference between what you start with and what you have to get just to get the reaction to go is given the value of E sub A, which stands for activation energy. Okay, so if the activation energy is high, the reaction is slow. If it's small, then it's fast. Should say if the activation energy is large. All right, so let's try this. Let's just, I'm going to move this down so we can see it a little bit more clearly here. So Nicole has a very good question. She says, exothermic reactions are spontaneous and endothermic reactions are non-spontaneous. The answer is no, 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 not always. Often, but not always. You have to count for delta S and temperature as well. Rather, I can see how you would have said, you would have come to that conclusion, Nicole. This kind of energy diagram can be used to represent heat energy changes, or it could also be used to represent free energy changes, right? Not that they are always the same, but it could be used to represent both of those types of energy changes, depending on what I put over here. So for the moment, let's look at free energy, right? This is a free energy diagram. We're going to look at free energy changes. Because this is lower, it's spontaneous than this guy, right? But the overall energy, just to get it started, is the energy of activation. All right, so we could draw a couple different examples just to kind of show you, because when I say large and small, with respect to activation energy, that's not necessarily super descriptive, right? So here we go. Here I have one with a what I would call a large activation energy, right? Still spontaneous because it's downhill from beginning to end, right? But probably very slow if it happens at all, because this activation energy barrier is just too high, right? So I would call this spontaneous but slow, right? Okay. In terms of it's naturally going to happen. Whereas if I had something like this as my energy coordinate diagram, how would you describe that? Spontaneous but fast, right? Good. Okay. What about, let's see. What about that? Non-spontaneous and also really slow. It would be hard to get over that barrier, right? And another option. So you can expect that I'll ask you a question like this on the exam. Like I could either give you an energy diagram and have you tell me what it's about, or I could give you the description and you could show which energy diagram would be the right one. All right, so this is non-spontaneous and fast. Right. Okay, so Sylvia says there's a question on the homework where you ask which diagram was slightly unfavorable. What did I mean by that? Unfavorable would mean that the products are higher in energy than the reactants, but only slightly. So this is a good example of a slightly unfavorable reaction. That makes sense. Yeah. Okay. Somebody asked a really good question. And that was, what if the energy levels are like about the same? Then what happens? Well, I am so glad you asked that question. I'm gonna scooch on over here to some blank paper and we'll talk about it. Okay. So what happens when your energy levels are so close as to be pretty much the same, and you have like a very small hill? So, you know, given ambient temperatures, everybody has enough energy to kind of go both directions. What you have then is a reaction which will naturally actually flow in both directions. And we call that a reaction in equilibrium, okay? Or that can make an equilibrium, reversible reactions. And what it does is it actually comes to what we call a dynamic equilibrium. I'll give you an example here. This is a reaction that you'll probably do if you take chemistry 1120. You'll do this in the lab. Take a carboxylic acid and an alcohol, you combine them, it forms an ester and water. And the energy levels of both of these sets are relatively similar, right? So you're like, which one is it going to make? Well, if you just dump them all in there and you stir it up, what you find is that you're going to get a big mixture that contains some of this and some of this and some of this and some of this, because some of it makes products. If you just dump in the reactants, then you start to form some products. And once you start forming a certain number of products, you're going to start making some reactants as well. And we call this a dynamic equilibrium. Equilibrium meaning that at a certain point, you're going to stop making any new products and reactants in terms of like total concentration. But it's dynamic in that the molecules are still there and they're always interacting with each other. It's just that the rate of forward direction of the reaction and the rate of the backward direction of the reaction are the same. So you could think of it like a store, right? A crowded store. People are going in and people are coming out at the same rate. This number of people in the store doesn't change, but the people who are in the store do change. Does that kind of make sense? Oh, excellent. Erica says you guys did an equilibrium lab this week. What did you do for your equilibrium lab? I'm not sure that I'm familiar with the equilibrium lab in particular that you guys do. You mixed acids, mixtures. Cool. We saw color changes and salts. Very good. Well, good. I'm glad that that at least for 1 week, everything is lining up. I know it doesn't always, your lab and your lecture don't always sync up perfectly. All right. But what you have is both the forward and the backwards direction. A good example of this, like in real life that you could think of, is taking a bath, right? If you're really dirty and you climb into the bath, then what you have is clean water, and here's mine. I'm just trying to get as warm as possible here in the bath. Stick figure. And I get in, and there's dirt all over me. Let's say I've been working out in the yard. I mowed the lawn. Okay. What's going to happen over time as I'm sitting in this bath? The dirt is going to move off of me and into the water, right? Okay, so here we go. I'm a dirty person plus clean water. And I'm going to represent this reaction. Here I'm going to get hopefully dirty water and a clean person, right? That's the hope. That's the ideal. Why we take a bath, right? Okay, so the dirt starts coming off of the person and into the water. Okay, so the person is a little bit cleaner. And some of it is even going to stick to the bathtub, right? Okay, all right. And we can add that to our equation. We've got a clean tub and then we've got a dirty tub. What's going to happen, 10 minutes in? The rate at which the dirt comes off the person is going to be matched by the rate at which dirt flowing around in the water hits the person and decides to stick back onto him, right? And so at some point, the water will have a lot of dirt in it, but is the person going to be totally clean? No, this is why we don't take baths, right? This is why you don't take baths to get clean, I should say. You might take a bath to relax because your muscles are sore after you've just mowed the lawn, right? Because you're getting old. But in terms of getting clean, once you're done with your relaxing bath, you're going to stand up and take a shower. And the reason for this is, as we look at changing ways to change and affect that equilibrium, there are some things that we can do to help push the equilibrium one direction or another. Okay, we will come back to this as we look at some of those reasons or the things that we can do to kind of push our equilibrium one direction or another. But hopefully this is an example that you guys can connect with. Okay. What we want to be able to do with this for just a couple minutes is do some math. You guys ready to do some math? It's been a little bit cerebral for the last couple days. We want to be able to predict, okay, are reactants favored, are products favored? If we know the concentration of each, about where is that balance? So to have that balance, we're going to come up with the equilibrium constant K. And I have this funny, this is directly from your lecture notes, and I need to edit it because it's wrong. Let me pull this out over here. Okay. So the equilibrium constant K represents the ratios of products to reactants, and this is nonsensical because I have M and N and this has C and D. So I'm just gonna replace these here. This will hopefully make a little bit more sense. CC plus DD. Okay. So you basically say, if I've got my reactants A and B and I'm making products C and D here, and the little ones are the coefficients, then the expression for K, the equilibrium constant for the reaction at any temperature, is going to be the concentrations of each of these things. That's what the brackets mean. So the concentration of my product C raised to the power of the stoichiometry number here. So in the balanced equation, A, B, C, and D are the coefficients that belong in front. So the coefficient is your power. So C raised to the C, D raised to the D, divided by A raised to the A times B raised to the B. So like for this equation right here, it's already balanced. All of my coefficients are 1. So the equilibrium expression just for this guy would be K is equal to, we have the concentration of the products, CH3, CO2, CH2, CH3, multiplied by the concentration of the other product here, H2O. Oh, out of space. Divided by concentrations of the reactants. Again, these brackets means concentration. And we are going to talk in chapter 9 about a lot of concentration units we might use, but here I'm just going to give them to you and we're going to apply them as is and not worry too much about it, okay? So this divided by that. We don't have anything to raise it to. There's no powers because there's no coefficients here. Does that make sense? So I'm just going to write this down here so I'm clear. The equilibrium constant K represents the balance, basically, of products and reactants at equilibrium. Okay. All right. So first things first, you guys are asking, do we calculate? What do I do with this? First things first, you will be required to come up with an equilibrium constant like this if I give you the equation. And then after we do that, we should be able to do some math with it, okay? So let's look at a couple examples here. Let's see if you can come up with the answer. Oops. Here we go. Here are two equations that have equilibrium. This should show equilibrium. Okay. All right. So in this case, if I have nitrogen dioxide, it is in equilibrium with dinitrogen tetroxide. This is just kind of a natural equilibrium mediated by a little bit of pressure. And if I follow this equation, I don't have two products, I just have the one, right? And I don't have two reactants, I just have the one, but the products go on the top, the reactants go on the bottom, and they're raised to their coefficients, which in this case, I've got a 2 here. So what does the equilibrium expression for this reaction look like? That's exactly right, Sarah. Perfect. We've got the products. Oops. Even in. Okay. Divided by the reactants. And that reactant has got to be squared because it has a 2 with the coefficient there. I'm going to make that a little cleaner here. Does that make sense to the rest of you? Just like that. That is it. This is the K expression, the equilibrium expression for the equilibrium constant K for this equation. All right. What would it look like for this equation? And again, this K expression is specific to this equation, right? So this K expression is not going to say anything about this reaction and vice versa. Okay. Hang on a second. We'll get there for a second, Sarah. Okay, so NO squared, good, times VR divided by NOBR. Good. All right. If I can give you the K value, then you can tell at a glance whether reactants are favored or products are favored. That's kind of nice, right? How would you know that? Just by looking at the K value. Oh, thank you. Here too. Good observation. Okay, because products are in the numerator and the reactants are in the denominator, you can say if I have a larger value for the products, then your K will be greater than 1. It'll be a bigger number. And if I have more reactants, for instance, let's say I have more products, let's say it's a 2-to-1 ratio this direction, then my K will be greater than 1 because my numerator is larger than the denominator. So K will be greater than 1. In this case, K would be 2. If instead I had more reactants than products, then my denominator becomes larger. And in this case, that's even squared. So that's going to be 1/4. So if my number is less than 1, it's because my denominator is larger than the numerator. So if my K value is greater than 1, products are favored. If my K value is less than 1, reactants are favored. If my K value is about 1, and actually, truly, if it's between, say, 1,000 and 1,000th, in that range, then we can say, hey, there's a measurable equilibrium here. Does that make sense? Okay, good. Okay, good question. You guys said, say that one more time, please. All right, so what we have here for the K expression is we have products divided by reactants, right? And when we put in the concentration, we're saying how much of each of those there are. So if there are more products than reactants, then your value is going to be greater than 1. Like if you had your products was 2 and your reactants were 1, then 2/1, your K value is greater than 1. Your K value is 2. That means that you have more products than reactants in your equilibrium, right? Whereas instead, if the ratio is the other direction here, right? If you had more reactants than products, now your K value is less than 1 because the denominator is a larger value. So you can tell by looking at it, if I said your K value is, say, 0.01, you'd say, whoa, that's less than 1. I think that actually reactants are favored. In fact, 0.01 is the same as 1/100th. So it looks like, roughly, it looks like there's 100 times more reactant molecules than there are product molecules in this equilibrium reaction. Does that make sense? It's a little bit tricky. You probably haven't practiced going back and forth between decimals to fractions, but that's exactly what, it's kind of the easiest way to see it here, right? If I say the K value is 0.01, that's not as meaningful as to say the K value is 1/100th. And then if you look at your original and say, well, if my products divided by my reactants is the same as 1 divided by 100, then I have a lot more reactant molecules than product molecules. Okay, so for example, all right. Sarah says, can't you just look at it if it's more disordered or ordered? No, this is a different thing than just entropy alone, right? Because this is looking at the total free energy change, and if it's close enough, then it'll go back and forth between the two. Okay. All right, let's practice doing just a few more of these. These first examples came from your homework. Sorry, not from your homework, from your lecture notes. Here are some from your worksheets, okay? Sarah says the bigger number is the favored one. Yes, because what we're putting in these brackets is concentration, right? And a higher concentration means you have more of that thing in the space. Remember, the reaction space is the same for both, right? These are happening in the same place at the same time. So if I have a higher concentration in that same space, then there's more of that thing. Does that make sense? Okay. All right. So first we're just going to practice writing equilibrium expressions, and then we're going to start doing math with them, okay? And it's just algebra, but it might have been a while, so we're going to practice a little bit. But let's just write these first, okay? So this one, I have two reactants, one product, but again, in the K expression, all the products go on top. All the reactants go on the bottom. No, Erica, all of these reactions are in equilibrium. Or at least we're talking about them as if they were. Like if they were in equilibrium, what would that equilibrium expression look like? Perfect. That is it, Sarah. Setting it up is the first step. And then as you become more comfortable with it, it'll make more sense, I think. So products is CO2 divided by reactants, which is CO times O2. And the CO2 and the CO both have to be squared. And I'm going to make some space for that to happen. Here. Just like that. Does that make sense? Okay, what about this guy? Perfect, Sarah. I'll get to your question in a second, Zach. Hang on a second. C2H4Cl2 and multiply that by HCl. Now that one's going to be squared. I'll come back to it in a minute. It's going to be divided by C2H6 multiplied by Cl2, and that one is also going to be squared. Excellent. Yeah, Sarah and Nicole both got that. Excellent. Okay, so Zach said, how do we know if reactants or products are going to be favored? Like, for example, in example A. The answer is without actual numbers to plug in, you don't know. So we're not quite there yet. We'll get there. But you actually don't have enough information to answer that question yet. Okay, what about this last one? That's kind of cool. This is oxygen in the atmosphere going to form ozone in the atmosphere. And light energy from the sun mediates this reaction, specifically like UV energy. Excellent. Good. And it's in equilibrium, which is good because we don't want all of our oxygen that we like to breathe to turn into ozone. We would die. But we don't want all of the oxygen in the atmosphere to just be regular oxygen because then we would all get sunburned. Okay, so the O3 is going to be squared and the O2 is going to be cubed. Okay, oh, that's your K. All right. Does that make sense? Do you guys feel like you could do that on the test? Guarantee there's going to be a question like that. I give you an equation, you tell me what the K expression looks like. Good. All right. I'd like to plug in numbers for these, but I actually do like to give you guys a break about halfway through. So come back in about 5 minutes and we'll do the math on these. Okay, picking up where we left off, we had just come up with equilibrium expressions, and now if I give you the numbers to plug in, we should be able to solve for this. So this is just an algebraic equation. They want to know K, and they've given me the values to plug in for the NO, the BR2, and the NOBR here. So hypothetically, this should be pretty simple, right? So K is equal to, if K is equal to the NO squared, that's going to be 0.1 squared, okay, multiplied by the BR2, which in this case is 0.050, in brackets, divided by, this is the first and the only time in this entire, maybe not the only time, this is the first time in this course that I will tell you it is okay to drop the units. K is a unitless value. We're not going to worry about canceling out, but everything should be in the same units in terms of concentration units here. All right, and that's going to be squared. Did I put everything in the right place there? Does everybody see where I got each of these things from? We said the NO was 0.1, so the NO is 0.1, and the BR2 that I needed right here is 0.05, so I just plugged that in there. And then the NOBR that goes on the bottom was given here, so I just plugged that in there, and now I just solve for K. For those of you that prefer the math part of these classes, you're going to enjoy this. Okay, so Sarah did this and she got 2.003. Let's confirm. If I put in 0.1 and I square that, and I multiply that by 0.05, it's going to get me 0.0005. And then divide that by 0.0158, and I'm going to square that, which gives me 0.0024964. Oh, I missed a zero. Okay, and I don't need to simplify it and then go, but just kind of wanted to make sure that we're on the same page here. Yep, 2.003. Excellent. Unitless value, just 2.00 is fine. Does that make sense? No units. As I said, Sarah, this is the only time that it's okay to drop the units, and then K is a unitless value. So you just say K is 2. And because it's greater than 1, we can say, roughly speaking, the products are twice as favored as the reactants. So for every 3 molecules running around, not for every 3 molecules, because there's more than that in this thing, but on balance, you're going to have twice as many product molecules as you have reactant molecules, to a first approximation. How do you know these numbers here? Zach, I'd have to give it to you, right? There's no way that you would just know those, so that you'd look them up or something like that. I'd give it to you. Okay, let's do it again. This is using the same reaction, and that means, of course, that I'm using the same equilibrium equation here. Now they want us to calculate the concentration of bromine if the concentration of NOBR is 0.016 and the concentration of NO is 0.1. Well, now I'm solving for BR2, and here's BR2. I have to get it all by itself. So to get it all by itself, just as a reminder, or just general algebra, we're going to multiply both sides by NO BR squared so that it'll cancel out on the right. There we go. Multiply by both sides, they're still equal. So this cancels with that. And then we're going to divide both sides by NO2 squared, sorry, NO squared, I should say. When I do that, the NO squared cancels. And I get that the K multiplied by the NO-BR squared divided by the NO squared is equal to the BR2, is how that simplifies out. So NO-BR squared divided by NO squared times K is equal to the BR2. We've done so much dimensional analysis in this course that it feels weird to be doing algebra, doesn't it? Sarah's got a great question. She says, would you even be able to do this equation if we hadn't already figured out that K was equal to 2? And the answer is no. You're going to use the fact that you know that K is 2 for this because it's the same reaction with these other values to plug it in. Good observation. So the NOBR for this one is 0.016. We're going to square that. Then we're going to multiply that by 2. And we're going to divide the whole thing by 2.1. We're going to square that. All right. How does it feel to be doing algebra, guys? Meh. You prefer dimensional analysis? Have I converted you yet? Okay, so we get a value of 0.0512. Does everybody agree? And this is going to be moles per liter because these other ones were in moles per liter. Okay. Yeah, I get that it might have been some time. That's why I'm spelling out every step along the way. Hopefully, if it's been a while since you've done algebra, this is going to be a little bit of a good review. In the case of this reaction, remember it's the K that determines if products or reactants are favored. So Sarah says, does this answer mean that reactants are favored? And the answer is no. Yeah, because the K is 2, that still tells us products are favored. This is just the value of the BR2, right? Not the K value. Good, good, good. Okay. So here are the questions on your worksheet. For the first one, they give you an equation and they give you the equilibrium concentrations, and they want to know what the value of K is. So this is just like the one that we just did. You solve for K. But in order to solve for K, you have to know what the equilibrium expression is first, which is why I had you guys help me to write equilibrium expressions. If I scroll up here, this one is actually the one that you just did up here. So we've already done this equilibrium expression. I'm not going to make you do it again. We can plug that in down here. This guy here. Stay there. Okay. So to solve for K, we're just going to plug it in, right, as we see it, right? We'll say, okay, well, the CO2 given here is the 0.11. Make sure that we are matching. Would be easy to mix up the CO and the CO2, for instance. And then the CO is this one here. And the O2 is this one here, right? Okay, so the CO is going to be 0.11. We're going to square that. And then on the bottom, we're going to have the CO, which is 0.025. And we're going to square that. And then the O2 is the 0.015. We're not going to square that. Be really careful to distinguish between coefficients, which make you square, and then just the formula, which might have a 2 in it, right? Which would not make you square it, obviously. All right. This is pretty straightforward. Oops. Oh, no, not at all. Squared. 0.025 squared, so divided by 0.015. 1290. That's really big. All right, so are products favored or reactants favored? Products are highly favored. Yeah, that's right. Excellent. All right. This was pretty simple because you just kind of have to plug it in, but it can be helpful to practice times when you have to solve for the thing first. So we're given this guy, N2O4, going to form 2NO2. Did we already do that one? Oh, we did the backwards version. Okay. All right, well, we have to come up with our K expression ourselves then. So in this case, K is going to be equal to, my products here are NO2. So I'm going to say NO2, and I'm going to square that, divided by my reactants, which here is the N2O4, right? Everybody agree with me? Okay. So if I give you K and I give you NO2, we should be able to solve for N2O4. And I'm going to tell you, many of you will be able to do this without issue, but there are a few of you who are going to do it wrong. And I'll show you what it is that you're going to do wrong, so you know not to do it, okay? It's tempting to say, look, if I divide both sides by NO2 squared, down here, if I divide both sides by NO2 squared, then actually my N2O4 will be all by itself, and I can solve for it and I'll be done. And that will be very easy. I'll have the answer. Is that the right answer? No, why not? What's wrong with that? Oh, perfect, Sarah. But something with algebra, we have to meet two conditions to make sure that we have the right answer. A, the thing that we want needs to be by itself, okay? get the thing that you want, we'll call it X by itself. But also get the thing that we want, in this case, we'll call it X on top, right? So the problem that we have in this instance here is that we're not solving for N204, we're solving for 1 divided by N204, right? So I specifically put this up here because I see this all the time, and I just want to make sure that you guys are understanding what that mistake is and how not to do it, okay? Yeah, so you could do this and then you could flip it and that would be fine. But just like when we're doing dimensional analysis, if the units that we want are on the bottom at the end of the day and they're supposed to be on top, then we haven't really solved it. We'll have to flip it, right? So this would be okay. Divide both sides by NO2 and then flip it. That would work, all right? But if you're like, no, flipping is weird, I don't want to do that. I just want to solve. I'll just leave that there. I just want to solve for the actual thing. Then instead, what you'll want to do, hang on. Oh no, I ruined my lovely little, okay. Instead, what you'll want to do is start by putting it on top instead of start by trying to get it by itself. So if we start by putting it on top, we're going to multiply both sides by the N204 just to get it on the top. Like, let's get this out of the denominator. All right, so here they'll cancel. And now that it's on top, now I can worry about getting it by itself. I'm going to do that by dividing both sides by K. There we go, K cancels, and I get that N204 is equal to the NO2 squared divided by K. Does that make sense? Really, algebra is all just about multiplying and dividing other things out of the way to get the X by itself and on top. All right, so now I can just plug this in. The NO2 value that was given here is 0.0250, and we're gonna square that, right? And then we're gonna divide that by the K value, which they told us is 7.2 times 10 to the negative third, or basically 0.0072, right? So 0.250 squared divided by 0.0072. There we go. And we find that the value for N204 is 8.68. And this is in moles per liter, so we'll also say moles per liter for the N204. Does that make sense? Okay. I will let you guys do this one by yourself because we still have to talk a little bit about equilibrium. But there is a little trick to this one, and that is when you're solving for NO2, note that here it's squared. So when you get it by itself and on top, it'll still be squared. To get it actually by itself, you have to do the inverse of a square. Do you guys remember what that is? It's the opposite of a square. The square root, yeah. When you take the square root of a square, like this, NO2 squared, then the square root and the squared cancel out, and that will get you the NO2 truly by itself. That's one that's a little bit tricky for students. I'm just going to let you guys do that one by yourself, but I want to give you a heads up on that one. Okay, so the last thing we need to talk about today is Le Chatelier's principle. I'm going to go back to, where am I? I want my little bathtub here. So Le Chatelier is he's a French chemist, if you couldn't tell by the name, Le Chatelier. There we go. Is that what they were trying to do in your lab, was talking about Le Chatelier's principle? Okay, that's all right. We'll talk about it. We'll help. So Le Chatelier's principle is looking at systems of equilibrium, reactions at equilibrium, true, but also other systems at equilibrium. So like this example of my person in a bathtub is a system in equilibrium. All right. And Le Chatelier says, look, if you've got a system that is at equilibrium, basically nothing is really changing in terms of overall concentration, because say the dirt is coming off of you at the same rate that it's going back onto you in the tub. If you're at equilibrium, if any change is made to the system, then that equilibrium will shift to counteract that imposed change. It's almost like things are trying to stay the same. And in a way, they kind of are. What we find is that this K value for this K expression, it's fixed at a certain temperature. And so if you change one of these numbers, then everything else is going to adapt in such a way to reestablish equilibrium where that K value is the same, right? It's going to just adapt. So everything is kind of not, I don't want to say resistant to change, but when you put in a change, it just adapts to counteract that change. So, like as for instance, I'll give you a couple examples of things that you could do to impose a change on something, and then what's going to happen. So the first thing we're going to talk about, and actually before I do that, I should probably write down what the Chatellier's principle is. Sometimes these are referred to as stresses, right? If an equilibrium experiences a stress, then it's going to move to relieve that stress. So the primary changes that you can experience would be concentration, pressure, temperature changes, and catalyst. So these are the 4 things we're going to talk about. Okay. Changes that can occur. So first of all, concentration. If you have a system at equilibrium and you increase the concentration of one of the products or reactants, then the system adapts by removing the product or reactant that you just added. How could it remove it? I'm giving it away. It's by that equilibrium reaction, right? So in our, hang on a second, let me see here. I'm going to pull this reaction. Pulling this reaction that we very first started with. It's another one. So if I'm running this reaction and it's in equilibrium, and I dump a bunch of extra alcohol in it, then it's going to remove some of that alcohol and use it to make more of my product. Basically what happens is if I add a reactant, then the system says, whoa, too many reactants, I'm going to remove some of those and make more of these with them. Means you're also going to remove some of those because it has to react with these, right? So on balance, the reactants together versus the products together, they'll still have the same equilibrium value as they did before, right? So when I say removing, I don't mean that you destroy it or that you take it out of the reaction. I'm just saying you have an equilibrium. So you'll basically offload it onto this side and make something different with it. So in the end, if you add a reactant, you're going to end up with more products. Or if you add products, you're going to end up with more reactants. Now, let's show it to you with this system, right? You've got a clean tub, dirty person gets in, clean water. All right, you reach some equilibrium point. If I add something to this side, if I had more of something on this side, let's say I added more clean water. Give another 10 minutes, equilibrium is reestablished. The person is going to be a little cleaner than they were before, right? Because some of that clean water is going to pick up a little bit more of the dirt off of that person. Does that make sense? Right, so adding a reactant is going to push it towards making more products. But the same is true of adding a product, right? Let's say I'm at equilibrium here and my 2-year-old son, bless his heart, walks in and is like, hey, we're having a dirt bath. And so he runs outside and grabs a bucket of dirt and comes in and dumps it in my bath water. Whoa, thanks, dude. I love little children. Okay, I have just added a whole bunch of extra dirty water to my previously established equilibrium. What's going to happen? Am I going to stay as clean as I was? No, that equilibrium will reestablish itself and some of that dirt is going to stick onto me and now I will be dirtier than I was when I started. That makes sense, right? This is why we take showers. Okay, now let's say we've got this equilibrium. What do you think will happen if you decrease the concentration of one of the products or reactants? How will the system adapt? You're going to make more of that, the product or reactant. That's right. And again, it's done by the equilibrium reaction. So one of the things that you can do on this equation here is you can say, look, what if when I run this reaction, I put in like a special little chemical, maybe some little beads or something that absorbs all the water. So when I hit equilibrium, I make some water, and then I come along and I remove the water, minus the water from the situation. Then the whole thing says, oh, well, I have to reestablish equilibrium. I'm going to do it by making more water. Here we go. So I'm going to shift, you could say shift that equilibrium a little bit that direction to make more of that. Of course, that's going to give me more of that, and you're going to lose a little bit more of that. And then on balance, because you've lost some of this and lost some of that, you will reestablish K. Does that make sense? Okay. In our example here, what you could do if you were like, listen, I really don't like showers. I'd rather just take a bath and actually get clean. If you set up a little filter pump here that pulled out water and pushed it through a filter and then put clean water back in the tub. Gosh, that'd be nice. Circulating water. You could heat it up while it's at it, right? And clean the water. So this is going to remove the dirt from the water. Then what would happen is as you're sitting there, more of the dirt would come off the person, right? That makes sense? All right. So that's how concentration change will affect equilibrium. If you're making more of, if you've got something in equilibrium and you dump something in, then it's just going to offload it to the other side of the reaction. Not completely, but just enough to reestablish K where it was. If you've got a reaction and you remove something from it, doesn't matter whether you're removing something from the reactant side or the product side of the equation, that equilibrium is going to shift to make more of whatever it was that you removed. All right, so that is concentration. Now pressure is kind of the same as concentration, but just for gases, right? So this worked well to describe what's happening in solution, But if you are in a gas solution, then pressure is how you would express concentration. And we'll talk about a little bit more about this in chapter 8. That is coming up. But let's just kind of write this down here. You have the same things about concentration, but also you will find that gases they take up space, right? And they exert pressure. And because gases take up space, what we'll find is that if there's less space available, then the equilibrium will actually shift to whichever direction has fewer gas particles because they take up less space, right? So here we go. If pressure is, okay, this is in a gas equilibrium, or I should say in an equilibrium system that includes gases. If pressure is increased, like as for instance, if volume is reduced, right, then the equilibrium shifts to the side with fewer gas particles because they take up less space and will exert less pressure. So they'll counteract the increased pressure that you added, right? And contra that, if pressure is decreased, like for example, if volume is increased, then the equilibrium shifts to the side with more gas particles, right? So got this example in your lecture notes. We have this system. Here we go. It's all gases, right? And it's balanced. And hopefully you can see, just look at the coefficients here, that you have a total of 3 moles of gases on the left for every 1 mole of gases on the right. So 3 moles of gases are going to take up more space or exert more pressure than just 1 mole of gases, because there's just basically less gases overall. So if you had this at equilibrium and you increase the pressure significantly, you should expect that it's going to move towards the side which is going to take up less space. Whereas if you have this system and you decreased the pressure significantly, then you might be able to induce it to form more of these reactants. Does that make sense? For these ones, I just literally want you to look at the total number of gas molecules on the left-hand side versus the total number of gas molecules on the right-hand side, and make your prediction based on that. If that makes sense. Okay. Temperature changes, as we already saw with collision theory, temperature can make a reaction go faster by giving somebody more energy. But in terms of the equilibrium, what you have to look at is this reaction exothermic or endothermic? Because exothermic reactions, heat is a product, and in endothermic reactions, heat is a reactant. And so increasing the temperature might just be the same as adding a product if it was exothermic, or increasing the temperature might be the same as adding a reactant if it's endothermic. So you can actually just put it back to concentration if you're looking at energy as a product or a reactant. So adding or removing heat shifts equilibrium for exothermic and endothermic reactions in the way you would predict using the concentration model. So like as for instance, this is going to be pretty straightforward. We see that liquid water will freeze and release this much heat energy. So if you added heat to a system that had both solid water and liquid water, okay, so here's your system. It's a plate. It's a dish that has an ice cube on it. And there's a little bit of melted water on the bottom. So you've got both of these things present in the system. And what's going to happen if you add a bunch of heat to this system? Light a fire underneath that plate. You're going to get more liquid water. That is something you know because you know something about ice. But if we're looking at our equations, we can say, oh, heat is a product of the reaction as shown here, right? If this is an equilibrium. So if I'm adding heat, just as I would expect, it's going to push the reaction the other direction, and I'm going to get more of that. Does that make sense? Excellent. Okay. Last thing we have to talk about is catalyst. And a catalyst, this is very important, it's going to be on the test. Okay. Catalyst, by definition, cannot change the equilibrium. What it does do, as we saw, is it will greatly speed up the rate of the reaction. So you can get to equilibrium faster if you have a catalyst. And you can maintain that equilibrium more easily because it makes it faster for the catalyst, but it doesn't change the equilibrium. It doesn't move anything from reactants to products. It doesn't change what's going on like these things do, right? If you put other stresses on it, then you might induce it to have a shift towards reactants or products, but catalysts won't do that. So this does not affect equilibrium. It only speeds up the rate. So it can help you get to equilibrium faster, but it's not going to change it. All right. You guys with me? That is it for chapter 7. We've got our test on Tuesday, I believe. Again, just like we did with the first 2, because we've been able to cover everything, we'll just spend a little bit of time on Tuesday going over the practice exam itself. And just as prep, and then I'll let you go early so you've got enough time to take the test. But that's it for chapter 7. If you've got any questions, you can hang out for a little while. Otherwise, I hope you guys have a great weekend.